With the superposition and the interference,
Yeah.
can you explain the stationary waves?
Yeah.
Like how the formation of them? I mean,
Okay. So to get stationary waves, come on, screen share is. Oh dear, is that sharing screen?
No.
not yet.
Not yet.
Now it is, yeah.
Yeah, now it is doing it now. Right. For that one, I need to get rid of here. Right. Stationary waves always cause a problem. When you get them in your head, they're dead easy. And the best way to do it is go back to absolute basics. And I was very, very surprised I didn't get more questions. I think one of the first people asked me really about the stationary waves because I want this one here. And I've got some beautiful demonstrations to show you, and I can't wait to do it. And I will get some demonstrations out the best I can when we are back in. Right. So stationary waves. Oh no, wrong one. That was didn't want that one. Go away from you. I think it's going to be one of these links will take me there. There we go. Go on. Yeah. Right. So in your stationary waves, you've got a wave and a string, yes? Now, what you've got then, you imagine here's a string, that grey. Okay, so that grey line there. So you make a vibrate, and what happens is the wave goes all the way over here. And when it reaches the end point, you get reflection, and that shows you the blue wave going back. Okay, happy with that, Paul? Yeah? Oh, Earthquake Paul, do you see me? So the wave goes up.
So it's two fixed points, and one of them's moved, and one end is moving.
So the fixed point is here. Well, not fixed point. You vibrate your string there or your slinky. The wave travels all the way along here.
Yeah.
When it reaches the far end here, it reflects, comes back to itself, and comes back along here. Now, this showing the wave going out is going to be in red, and the wave coming back is going to be in the blue.
Okay.
Okay. Now, obviously, then the red and the blue are going to interfere with each other. So what you then get.
Why does the blue? Why is it a pi out of phase?
Right. The reason why it's going to be pi out of phase is because if I freeze a second, we at this point here.
Yeah.
There can be no vibration at all. Has to be.
Yeah, it's flat.
Well, the only way it can achieve at that point zero vibration whatsoever or zero amplitude if the two waves are out of phase by pi 180 degrees. So literally what happens is at this further point here, up here, you get a flip of 180 degrees, and unfortunately simulation doesn't show it, but there you get constructive interference, and it has to happen to make that, we call it a node. We've got no vibration. Okay. So as the red wave goes out, it hits this point here, it gets split by 180 degrees and then travels back. So what you then get is an interference pattern of the red and the blue. So to freeze it, using at a certain time here, you then at any time add the red and the blue wave together. What you then get hold of is the black wave. And this is the standing or the stationary wave you see. Now, the reason why that is zero here, because this goes up by that much, say plus whatever, and that goes down by minus. That plus that equals zero. Exactly the same this point here, that plus that equals zero. But this point where I can have going to be here, that point, you add the two waves together. It's probably better to skip forward a little bit. So what you get hold of, and I'll skip it goes really big. Now you've got a massive point here because you've got the red and blue at that point there. Therefore, the wave is going way up here. So what you end up with, and it's easier in some respects if I don't merge them, the red and the blue wave add together to give this stationary wave, which is the wave in the black.
Mm-hmm.
We then, this point here and here and here are always going to be nodes because they always add up to zero. This one then is called an antinode because it shows the point on maximum displacement, but the antinode changes with time. Therefore, it goes up and down like this. And literally what you get is a stationary wave, and the stationary wave is resultant of these two waves. Now it's called a stationary wave because number one, it's not going anywhere. This is a traveling wave, transferring energy going across there. And this is a transfer wave going energy from the right to the left. A stationary wave is a wave that we say is not transferring energy because it's stored energy in the string. It's not moving to the left and to the right, but it changes with time. And the formation comes of two waves going here. So we call always these points here are simply then going to be your antinodes. These points here are going to be nodes. But we did ask about the video about this. We always say then between adjacent loops, which is this loop here and that loop here, because that is always up and that one's down. And when that one's up, that one's down. There's 180 degrees phase between that point and that point. Yep. And then you got this forming here. Does that show you how stationary waves form?
You know how you said the blue one doesn't show something? Can you draw that?
Yeah. What happens is, and I need to go stop sharing a second, go back to my board. It's really annoying it doesn't do it. If I had got my, I'm actually going to get a black pen. I've got so many pens here. Which one to grab? There's my, oh dear, get the angle orientation. There's my wave going out. This, okay. When I pluck it, boom, the blue wave goes out like this.
Okay.
Okay. But when it hits here,
yeah,
okay, then it gets reflected, and to show the reflected wave, the red does that. It goes up. And the reason why it must start going up, because you've got to show the phase difference. There's got at this point here, there should be 180 degrees flip between the blue and the red.
Why that? Why is that?
Because at that point just here,
yeah,
I can't have any wave at all. Because I've got a one wave going up plus one wave going down. Because then I get my deconstructive interference.
Is that because it's like a fixed point?
Yeah, because it's a fixed point. And it naturally flips it to make sure that fixed point
doesn't move.
It's going to have zero. And that's why when the wave comes back,
is it because the point doesn't move, that's the only reason it flips?
Yeah, it's a fixed point. Yeah, because it can't vibrate at that point. And if you can do that, it's making 180 degrees out of phase.
On the nodes where the antinodes are in the simulation, why isn't it flipped?
Well, in the simulation you got here, you then got it changing with time. What we do is do a dotted line like this. But there's your resultant stationary wave. And it's showing change with time, yes? Basically, that stationary wave is a combination of one wave going to left and one wave going to right.
Can you finish drawing the red one? I don't get it.
Yeah. Oh, draw my diagram again. It's very hard to make it very, very neat going out. So what you've got to appreciate is going from here. Here's the wave. There's my bit I vibrate to make it go up and down.
Yeah.
Okay. There's going to be your wave traveling out like this. Whoop. It hits that point.
Yeah.
Therefore, when it flips, then you get 180 degrees and it starts coming about like that. I mean, and then you start adding the waves together. Okay.
Okay.
It has to point 180 degree flip because it has to flip that point there. But you got to remember then this wave is a snapshot of that time. But it must be 180 flip there because it must make this
a node.
Zero. But also remember that can cut off there because it could be that part of the phase. Therefore, the red now is going to be here.
Right. So then can you just draw it like a half second later? Or do it like a half second?
Now to show you that, I think this will help you. Oh dear, I want to do that. I now want to go back to my screen. Are you back in the simulation now?
Yeah.
Cool. Right. Now these things, I think I've included this on the Edmodo. I'm sure I have somewhere. So this shows it better. This is a snapshot in time. okay, where your black is your wave, stationary wave at time 0, just like a snapshot, okay?
Yeah.
And that happens because when it flips going that way, it's going to show you better actually. Here's A and B.
Mm-hmm.
That wave is hit here and then it's coming back. So that wave was about to go up. When it reflects, it starts going down. There's the 180-degree flip. And if you add the two waves together, you get the resultant wave. So therefore, that's amplitude 1 and the other one's 1. The amplitude is going to be 2. Okay? If I then start making time go further, at this point here, this B wave is traveled out and it's hit here.
Yeah.
You see the flip going up there. There's a 180-degree flip, and now it's coming back. I can't remember which color I use now. That's the wave coming back at itself.
How can it come back out of phase though? I don't get that.
Because you got that flip 180 degrees, because that bit going up,
Yeah.
the bit going down makes 0.
Right. Okay.
0 here.
Is this situation only happens when the first wave B doesn't end up doesn't complete like one wave
Yeah,
left.
it can arrive here at any point.
Okay.
Yeah, so it's good. This B is changing with time. So now when they return, you now add up the dotted and the dotted together.
Yeah.
So say example, this point here, you got the B and A added together, which comes down here. At this point here, you see this wave here, which is B, is 0, but A has got that amplitude, therefore 0 must be the amplitude of A that goes here.
Yeah.
Therefore, as you go through your cycle, it's a quarter of a time. Always, well, there's a quarter.
Mm-hmm.
Halfway through the cycle, you're going to have it at that 0 point here, because before it was down there, now it's gone up. Therefore, start taking the wave. I put this on Edmodo for you, and you start seeing how the wave builds up with time.
So it's literally it's just dependent on the time and how far it actually whether the first wave can actually travel a wavelength or not.
Well, you've got to remember it's a traveling wave, isn't it? What you've got to remember is as A and B travel out here, they go up and down. Therefore, the wave is going through. So at that point there, you get, I'll go back here. I think I see where you're sharing a second, where it's a good question you've got. You do think this very deeply. As your wave travels out, okay, any traveling wave does this, isn't it?
Yeah.
Therefore, if you say example, let's say this is going to be a water, and here you've got a duck at that point there.
Okay.
Duck move up and down with time.
Yeah.
This wave is traveling up. At this point, it's going to be here. Then that part of the wave is going to reach there.
Yeah.
Part of the wave is going to reach there. So this wave is a traveling wave. Therefore, this, like a little duck in the water there, is going to go up and down, up and down, up and down like that. Yes?
Yeah.
And all that happens is when it reaches there, you get that 180 degrees flip. Simple as that. Does that make sense, Paul?
Right.
Don't get too deep into it, but we can do it. We can do this with traveling waves. You can do it sound waves. I mean, I'll show you quite a cool demonstration. Where
can you go to C on that document? Can you go to C? Example C.
This one going down here. This one.
Yeah, C. Yeah.
Now, C. All that's happened is
right
through a cycle. Therefore, say this is up here. We say this is time 0.
Yeah.
Quarter of a cycle, half a cycle, 3/4, back here again. So on this one here on C, now the wave has gone, basically B's traveled out.
Right.
On here. Then you get your 180 degree flip and it's traveling back. And now what we got is we got no displacement at all, because here, this wave B has gone up.
Yeah.
Wave A has gone down. Plus that much, minus that much is going to be 0. Therefore, you got an antinode.
So what does a quarter time represent? As in, what does time? I don't get what T is. What's T?
Right. What we say, say you've got your stationary wave.
Yeah.
0 time, it looks like this.
Yeah.
Go all the way down. Go all the way back up again. We say is 1 time period. We then say quarter goes down here, half, 3/4, full cycle.
Okay, so it's like it's like the equation with the 1/3 frequency, right?
Yeah, I mean, you're defining what a cycle is. So if I go back in, go on the simulation again, it's like you're going from catch at the top, 0 time.
Yep.
Sorry, half a cycle,
Yeah, and then
3/4,
and
full
1.
cycle.
Yeah.
It's a way that they can ask questions to show the cycle they're going through.
Right. Okay.
That makes sense.
Yeah, kind of.
It's just showing you the cycle.
As much
And
as
then I think you asked this one yesterday. When you start showing waves in a string,
yeah.
this is basically your waves traveling out like this, and then you start getting the harmonics coming out, and this is going to be your 15 hertz, which is the first harmonic, which I said before, that's the 1i.
So is 15 hertz just universally the first harmonic?
No, it comes down to equation, and this is where guitars come from. The actual 15 hertz is dependent on the speed of the wave,
And the thickness of the string.
And the length of the string.
Right. Okay.
That's why.
Is that what that equation was yesterday?
Well, the equation shows, what it was going to be, because it's all to do with the length of string and the frequency, and that's why. Well, you know what ukulele guitar is.
Yeah.
A ukulele is quite short, isn't it?
Yeah,
and
it is, yeah.
Guitars are quite long. Therefore, well, like a double bass, or whatever it is, depending on the length of the string, that will depend on the fundamental frequency, and that's why also some strings are heavier. So that length here is dependent on the string itself, tension, etc. Therefore, that's going to be your first harmonic, and then I'll go in slow motion. Then this one pops out here where you got 30 hertz is going to be your 2i's I mentioned before, and that's why you get the full wavelength coming in. Yeah.
Yeah.
Were you happy with this bit, Macy?
Yeah.
See, you're happy with that? You happy that this is what I do in the lab, and I think I showed the simulation on the videos, didn't I? And then you got the 45 going up here, which is going to be 1.5 waves coming out.
When you take it off the slow motion, is that what you see in real time?
No, no, slow motion is literally Jacob's slow motion.
Right, okay.
What I do is I use a strobe in school, and a strobe allows you to see it. I will do it. I'm still debating. We go back in. Will I be able to get my hands on kit or not, or is it going to be so stressful? Probably not. But I have got a beautiful Rubens tube does this, but I'm going to have to try and work out logistics. But I'm somebody I learn by seeing as well, and I just can't rely on simulation all the time. I like to see it in real life, and I can show you in real life happening because it's absolutely beautiful to see. But there's a beautiful bit of theory of this, because you may, and Jacob, you'll be interested, I know you will be, is string theory. Have you heard of a string theory at all?
Is it the one where everything's made of tiny little strings?
Yeah, it's got an idea that particles are made out of strings, and it all ties up with stationary waves, which is a beautiful bit of physics. It's not been proven, mind. Also, it works in 16 dimensions. I travel anybody to work in 16 dimensions. I get lost in that. But the idea is particles will be represented like waves in a string, and we're waiting to see if it's confirmed or not. But there you go.